Good morning, students. Myself, Anupam Mittal, working as the Assistant Professor in Electrical Engineering Department of Shahid Bhagat Singh State Technical Campus, Firozpur, is here presenting my lecture on a very important topic of Power System 1, that is the performance of transmission lines. First of all, introduction about what is a transmission line. In an electronic system, the delivery of power requires the connection of two wires between the source and the load. At low frequencies, power is considered to be delivered to the load through the wire, and in case of microwave frequency region, power is considered to be in electric and magnetic fields that are guided from place to place by some physical structure. Any that physical structure that will guide an electromagnetic wave place to place is called a transmission line. Now, depending upon the length of line, the transmission lines can be classified into three categories. First category comes as the short line, second is the medium length line, third is the long line. Under short line, the length of line is shorter than 80 kilometers. They have negligible shunt capacitance, that is, we can neglect the shunt capacitance in case of short lines, and may be represented by their series impedance only. So, while considering short lines or while making the calculation of these short lines, we will consider on the series impedance in the circuit, and we will be neglecting the shunt capacitance on the shunt admittance part in case of short lines. Second category comes as the medium length line. In these lines, the length is a range of from 80 to 200 kilometers. That is the range. Length should be greater than 80 kilometers, but should be less than 200 kilometers. Then the range comes under the medium length line. These length lines may be represented by nominal T or pi equivalent circuits. Third category is the long line. Its length is more than about 200 kilometers. For these lines, the distributed effects of parameters are significant. We have to consider the impedance, the admittance part to be uniformly distributed over the line, or they have to be represented by equivalent pi circuits. Another method is to calculate the values of long lines, or to solve the problem of long lines, we may represent the cascaded sections of shorter lines with each section represented by nominal pi equivalent circuit. Now, here the diagram shows a long line in which we have distributed the smaller sections of lines. So, the combining these smaller sections of T and pi, we can contribute a longer line that can be resolved to solve a problem. Now, various transmission line models, that is of shorter line and of that of medium line, they can be represented by these two different diagrams. The first one, the diagram containing two port network of a network having resistance and inductance in the series impedance form. Shunt admittance has been neglected. So, this is of a short line model. Here upon the sending end, we have two ports and it is delivering a voltage Vs at the sending end. At the port 2, we have the receiving end, and here is a voltage Vr. So, for the overhead lines which are shorter than 80 kilometers can be modeled as the series resistance, that is R, and inductance L. Since the shunt capacitance can be neglected over the shorter distance, so model form is shown in the diagram. The inductive reactance at 60 Hz for overhead line is much larger than the resistance of the line. So, L will be of significant figure in case of shorter line. For medium length lines, the range ranging from 80 to 200 kilometer or 240 kilometers, the shunt capacitance should be taken into account. So, that capacitance can be taken as the two half sections, one is considered at the sending end and second part is considered at the receiving end, then that forms a pi network. If we consider the whole capacitance at the middle of the line, then that network or that model will be called a T model. And in case of longer lines greater than 240 kilometer or 200 kilometers, the longer lines are classified and they are to be discussed later in the lecture. Now, various parameters that are considered to be the important parameters of a line: the total series resistance, series reactance, and shunt admittance of a transmission line can be calculated as R is equal to small rd, where small r is the resistance which is per unit length and d is the length of the transmission line. So, if we have assumed that small r or small x and small y, these are the resistance, reactance and shunt admittance values per unit length, and d is the length of the transmission line, then we can calculate the total r, the total x and the total y over the line. Resistance total r is equal to small r into d, the resistance per unit length into the length of the transmission line. Similarly, x is also capital X is equal to small x into d, and capital Y, the shunt admittance, is equal to small y into d. Now, for the making of analysis of long transmission line, we have to assume some assumptions. The first assumption is, or the first point that we have to kept in mind is, the line constants, that is resistance, inductive reactance, the capacitive susceptance B, and the conductance part, they are uniformly distributed over the entire length of the line. R and X, they are considered to be the series elements and they will be represented as the series branch of the model. The capacitive susceptance B and the leakage conductance G, these are the shunt elements. The leakage current through the shunt admittance is maximum at the sending end and decreases continuously as we move towards the receiving end, and it becomes 0 at the receiving end. So, the value is decreasing moving towards right hand side, that is the receiving end, and it becomes 0 at the receiving end. Now, for the analysis of a long transmission line, let's we have a line whose two ports, one is the sending end port and second is the receiving end port, they are given, and over the entire length of the line we have considered a small length element dx over the length of the line, which is at a distance x from the receiving end. So, if we consider that small z is the impedance of the length of the line per unit length and y is the admittance per unit length of the line, and for the length dx, z dx will be the element considered and y dx will be the shunt element value considered. Now, taking the z to be the series impedance of the line per unit length, y to be shunt admittance of the line per unit length, V is the voltage at the end of the element towards the receiving end, V plus dV, that is V plus some more voltage dV due to the smaller element, voltage at the end of the element towards the receiving end, I plus dI is the current entering the element dx, I is the current leaving the element dx. So, if I plus dI is entering into the element z dx, then the current which is leaving the element z dx is value of I, that is it means dI current value has been used in the shunt element. Similarly, if voltage V plus dV is before the z dx element and V is the voltage which we are getting after the element, so dV is the voltage that has been used in the z dx element as the voltage drop. So, if we consider z dx is the total series impedance, y dx is the shunt admittance, then dV, the voltage drop, will be equal to current into resistance value or current into impedance value. So, current is I and z dx is the impedance value of the line. So, dV is equal to I z dx. So, taking the ratio, dV by dx is equal to I z. This is the equation number 1. Now, consider the element current I plus dI which is entering into the element and I is the value which is leaving the element. So, dI is the current which is flowing through the shunt admittance of the element. So, we can write that dI is the current through shunt admittance of the element equal to V by dx. So, current value is equal to voltage into impedance value, voltage divided by impedance, and voltage divided by impedance is also equal to voltage into admittance. So, V by dx is equal to dI, or we can write that dI by dx is equal to Vy. Mark it as the equation number 2. Now, take the differential of the equation number 1 with respect to x, then we will get the d2 by dx2 is equal to z di by dx, because we have the equation dv by dx equal to iz. So, when differential is taken of this equation with respect to x, this will become d2y by dx2 is equal to I into dz by dx. Now, when we put z into di by dx, this equation can be substituted as the equation number 2, where di by dx is equal to vy. So, substituting this value in the equation number we are using, so that will be z into vy. So, d2y by dx2 is equal to yz into v. Now, upon solving this equation, we will get the solution of the equation as v equal to k1 times cosh x root of yz plus k2 times sin of x root of yz. This is the solution of this equation. Yz, the under root of this yz will become the angle value of the cosh value. Now, if we take the differential of the equation of v, that dv by dx is equal to k1 times root of yz sin of x root of yz plus k2 root of yz into cosh of x root of yz. Now, dy by dx is also equal to iz. So, substituting this value equal to iz, we can get iz equal to k1 times root of yz sin of x root of yz plus k2 root of zy into cosh of x root of yz. From this equation, we can get the value of I by taking the z in the denominator of the right hand side term. So, when z is taken in the denominator and root of yz is taken common, we can write y divided by z under root multiplied with k1 sin of x root of yz plus k2 times cosh of x root of yz. Mark it as equation number 5. Now, in the equation number 4 and 5, the expressions for v and I are in the form of unknown constants k1 and k2. So, we have to calculate the values of these unknown constants k1 and k2. For that, if we consider that at x equal to 0, that is at the receiving end, because we have marked the distance x from the receiving end. So, at the x equal to 0, it means we are at the receiving end. V is the voltage equal to VR, I is equal to IR. So, putting these values in the equation of V, we will get V is VR equal to k1 times cosh of 0 plus k2 times sin of 0. So, this becomes k1 plus 0 equal to k1. So, the receiving end voltage VR comes equal to k1. Similarly, by putting x equal to 0, we get V equal to VR and I equal to IR in the equation number 5 of I. So, I is equal to IR is equal to root of y by z k1 times sin of 0 plus k2 times cosh of 0. This becomes root of y by z into 0 plus k2. So, we will get that the value of constant k2 is equal to z by y under root into IR. So, k1 is VR, k2 is root of z by y IR. Substituting these values in the equation of V and I, we will get that V is equal to VR into cosh of x root of yz plus z by y under root of IR into sin of x root of yz, and equation of I will become y by z under root into VR into sin of x root of yz plus IR into cosh of x root of yz. Now, if we substitute that x is equal to L, we will get the end which is sending end. So, V is equal to Vs at the sending end, I is equal to Is at the sending end when x is L. So, substituting the value of V equal to Vs here, I equal to Is here and x equal to L, we will get the two different equations, that are Vs equal to VR into cosh of L into root of yz plus z by y under root into IR into sin of L under root of yz. Similarly, Is is equal to y by z under root into VR into sin of L into root of yz plus IR into cosh of L root of yz. So, these are the two standard equations of the transmission line model, where sending end and receiving end voltages have been derived with the relation Then sending end voltage and sending end current, they are described in the values of VR and IR, that is the receiving end voltage and the receiving end currents. Now we can also substitute the value of L into root of YZ by equal to L, which is just out of root of under square root value. When it is taken under the square root, it will be L square. So taking the L, one with Y and one with Z, it comes Ly into Lz under root. So we can write that L into small y is capital Y, L into small z is capital Z. So similarly, small y by small z under root is equal to multiplying L both in the numerator and denominator terms of y by z, we get YL divided by ZL under root. So this is capital Y by capital Z under root, where Y is the total shunt admittance of the line and Z is the total series impedance of the line. So substituting these values, the equation of Vs and Is will become Vs is equal to Vr into cosh of root of Yz plus Ir under root of Z by Y into sine of root of Yz. And the equation of Is is equal to Vr into root of Y by Z into sine of root of Yz plus Ir cosh of root of Yz. Now next comes the generalized circuit constant of the transmission line. In any form terminal network, input voltage, that is the sending end voltage, and the sending end current, input current, can be expressed in terms of output voltage and output currents. Incidentally, a transmission line is a 4-terminal network, 2 port terminals where power enters the network, that is the sending end, and the 2 output terminals which shows the power leaves the network, that is the receiving end. So if we consider the 2 port network of a transmission line, we will get that Vs is the sending end at one port and at the receiving port is the output terminals. So if Vs is the voltage, Is is the sending end current and Ir is the receiving end current, Vr is the receiving end voltage. So as we have described in the long line model, that Vs is represented in terms of Vr and Ir and Is is represented in terms of Vr and Ir. So we can write that we have a generalized equation of Vs equal to AVR plus BIR and Is is equal to CVR plus DIR, where A and D are the dimensionless quantities. A constant B has the units of ohms and a constant C has the units of siemens or mho. So these A, B, C and D, these are the called generalized circuit constants or the ABCD constants of the line. Now if we take the equation of Vs, that is AVR plus BIR, Is equal to CVR plus DIR, then the different meaning, the values of symbols, Vs is the sending end voltage per phase, Is is the sending end current, Vr is the receiving end voltage per phase and Ir is the receiving end current. So this is the generalized form of equation of generalized circuit constants representing the different values of voltage and the current at the sending end in terms of voltage at the receiving end and the current at the receiving end. Now there are some values that we can, how A and D, they are been shown that they are dimensionless quantities. B is shown as the ohm value. The derivation is as shown in the slide. ABCD constants are generally complex numbers, and A and D are dimensionless. B and C, they are having units of ohms and siemens respectively. Now derivation point of view, we can see the slide line that at the receiving end, when receiving end is open circuited, that IR is equal to 0 value. So in the equation of Vs, Vs is equal to AVR plus BIR, but we are substituting IR equal to 0. So we are getting that Vs is equal to AVR, or we can write that A is equal to Vs by Vr. As A is the ratio of the voltage quantities at the sending end and receiving end, so it is a dimensionless quantity. So it has been proved that A is a dimensionless quantity because it is the ratio of the voltages of sending end and the receiving end. Now substituting IR equal to 0 in the equation of Is, so if we substitute IR equal to 0 here, Is will be CVR. So Is is equal to CVR, or C is the ratio of Is to Vr. So C is the ratio of current to the voltage, that is the units of reverse of impedance value or the units of admittance. So these are units of mho or siemens. Then for VR equal to 0, that is the receiving end is short circuited, we will get the equations equal to, so when VR is 0, Vs will be BIR, Is equal to DIR. So using these values, that Vs is equal to BIR, this implies that B is equal to Vs by IR. That is the ratio of voltage to the current, so it has the units of ohms. Similarly, from the equation of Is is equal to DIR, or D is equal to Is by IR. So again, D is the dimensionless quantity because it is the ratio of the sending end current to the receiving end current. So A and D, these are the two dimensionless quantities. B has been proved as the having the units of ohms, and current and the value C has been units of siemens. Now let us consider a short transmission line and modeling of the short transmission line. So the per phase equivalent circuit of a short line has been shown in the diagram. Here one port is showing the sending end port, and the second port is showing the value of output port or the receiving end port. If Vs is the sending end voltage and Vr is the receiving end voltage, and series impedance is represented by the series combination of R and L, so we have written R and L in the series form. Now we have already said that Vs is the sending end voltage, Vr is the receiving end voltage, Is is the sending end current, IR is the receiving end current. Because the delivered current from Vs end is as such passing to the port 2, that is the receiving end port, so we can say the sending end current Is is equal to receiving end current IR. So Is and IR is same in case of short transmission line. From these two equations, we can write the receiving end voltage Vr, which is lesser than the value of Vs due to the drop across R and L. So we can write that the value of Vr is equal to Vs minus the drop across R and L. So drop across R and L can be written as IR and IXL. So we can write Vr is equal to Vs minus Ri minus jXLi. Or manipulating this equation or rearranging this equation, we can write that Vs is equal to Vr plus Iz, where Z is the total impedance or total series impedance of the line. Expanding this, Vr plus IR plus jXLi. So this is the equation of Vs in case of short transmission line. Now if we consider the short transmission line represented by Z and containing a resistance part and an inductance part, now we want to form the equations of the transmission line of short line in terms of sending end voltage and sending end current, so that they can be generalized with the equations given of generalized constants equations. So in the first form we have said that Is is equal to IR, say this is the equation number 3 representing the equation of Is. Similarly, Vs is the equation of voltage at the sending end. Vs is equal to Vr, the receiving end voltage, Vr plus Z into IR. So this is the equation number 4. Comparing these equation number 3 and 4 with the equations 1 and 2, which are in the generalized circuit constants form. Vs is AVR plus BIR, Is is CVR plus DIR. So comparing this equation number 1 and 2 with 3 and 4, we will get that in the equation of Vs, AVR is written in the first equation. In equation number 4, it is written VR only. So we can say that value of A is 1 and value of B constant is equal to Z. Similarly, in the equation of Is is equal to CVR plus DIR. Here in the equation of Is, VR term is not there, so it means C is 0, and DIR term is here in the terms of IR, so D is 1 here. So generally in case of generalized circuit constant values, A comes equal to D. So instantly A is equal to D, and if we calculate AD minus BC, this is also equal to 1 value, because A into D, this is equal to 1 into 1 minus B value is Z into C is 0, Z into 0 0, so 1 minus 0 is equal to 1. So AD minus BC is also equal to 1 in case of generalized circuit constants. Clear? Now if we draw the different phasor diagrams in case of short transmission line. So first of all we will consider that the load is of lagging nature. Load is of such a nature that the power factor is of lagging nature, and the current is lagging the voltage VR by some phase angle. So if we consider VR is the reference vector and I is the vector which is lagging the voltage vector by some angle, then Vs is required to be obtained, which is VR plus IR plus IXL plus jIXL equal to Vs. So in the vector form, when we want to represent Vs, we have to add VR with the negative vector IR. IR is a vector which is in line with the I vector. So if I is here, so IR is the parallel line which is in parallel with I. So VR is getting added to IR. Then jXLI is the term which is perpendicular to IR term. So we have drawn a perpendicular upon this line of IR. So we are getting another vector which is jXLI. So if we add VR, IR and jXLI, we are getting a new vector which is called Vs vector. In case of unity power factor of the load, if VR is the voltage, receiving end voltage, and it is taken as a reference vector, then current I is the vector which will be in line or which will be in phase with the voltage VR. So if we want to add IR vector which is in phase with I, so we are getting VR added to, we are getting a vector VR which is added to IR vector, inline vector. Then jXLI is the vector which is perpendicular to IR vector. So we have getting this vector as the Vs vector. Similarly, for the leading power factor case, if VR is the voltage as the reference vector has been taken and I is the current which is leading the voltage, so we have to make a vector which is leading the VR vector. So we have marked I vector as shown in the diagram. Now a vector parallel to I vector will be added to VR for making IR quantity. So VR plus IR, and a vector perpendicular to IR vector is jXLI vector. So we have marked here. So VR plus IR plus jXLI is equal to Vs. So in all the three cases, Vs is the voltage, lesser value of voltage in case of leading power factor case. For a given source voltage Vs and the magnitude of the line current, the receiving end voltage is lower for the lagging loads and higher for the leading loads. Or we can say Vs is lesser in case of leading loads and VR is more in case of leading loads. Now next is the modeling of the middle lines. In case of middle lines, we can use two methods. One is the nominal T method and second is the nominal pi method. The difference between the two is, in case of nominal T method, we will be considering the shunt admittance part as a lumped part and it will be connected across the middle of the line. Half series impedance will be connected before the shunt admittance part and half will be connected after the shunt admittance part. But in case of pi circuits, we have to take the shunt admittance into two parts, half of the two sections. One half section will be considered at the sending end and series impedance will be fully taken as the one part, and then shunt admittance at the receiving end part. So in case of nominal T method, say we have Z as a total series impedance, then Z by 2 will be connected before the shunt admittance and half will be connected after the shunt admittance. So if Vs is the sending end voltage, Is is the sending end current, this is half series impedance, this is again half series impedance, IR is the receiving end current at the load with value of the voltage equal to VR. If IC is the current which is going through the capacitor or the shunt element and V1 is the voltage across the capacitor. So we can write different equations of the voltages by using KVL. Vs is equal to value of the voltage is equal to the value of voltage V1 at the shunt element plus the drop across Z by 2 element. So we can write that Vs is equal to V1 plus Is into Z by 2, and the value of V1, now this value of V1 will be Vr plus Ir into Z by 2. So we have written here V1 is equal to Vr plus Ir into Z by 2, and the value of the capacitive current IC is equal to, if we apply KCL at this node, then Is is the sending in current which is incoming, then IR is the outgoing current, IC is the outgoing current. So we can write Is